Hey everyone and welcome back to another tutorial. I'm CodeWithAhsan and in this video you are going to learn about binary search trees. Now this video is a series of data structures and algorithms and I have many more videos that you can also watch as well. But this one is going to focus on BST or binary search tree and we are going to see how to implement that within JavaScript. Before we go forward, I would like to do a quick shameless plug. I wrote this really cool book called Angular Cookbook, which is one of the best books out there right now to learn Angular, especially if you are looking to upgrade your skills for enterprise web applications. It has topics from Angular animations to Angular performance and whatnot. So if you want, grab your copy. You should be able to see the link in the description. And if you have not subscribed to the channel right now, do it and let's move forward into seeing how to implement the binary search tree. Now, as I said, this is part of my video series. So these are all the fun projects that we have created so far, but this binary search tree is the one that we are going to look at today. And this is beautiful. I actually enjoyed working on this one live on the stream and I also taught how to build it, but this works amazingly fine. So what is a binary search tree? So a binary search tree is a tree which has essentially two nodes or two child for each node. So it could have two child, it could have one child, it could also have no children at all. So here you can see that every element has at most two children. One more important thing to know is that every node has its left child having a value lesser than the node itself. For example, see this node 5. So this 5 has the left child which is 3, which is less than 5, but then it has 6 which is greater than 5. Similarly, this 5 has a parent which is 7. So 7 has a left child which is 5. So 7 is greater than 5. Similarly, 9 is greater than 7. So 7 has a left child which has a lesser value and a right child which has a greater value. Similarly, if we have a look at 9, you can see that 9 has a left child of lesser value which is 8, but 10 as a greater value. So this is how the whole tree comprises itself, that every left element has a value which is lesser than the node and every right child has a value which is greater than the node, and that is how it works. So as I said, it could have one child or two children or no children at all. Now, how do we look at this whole BST tutorial? First, I'm going to show you what the final output is, which is right now what you see, but we are going to look at the functions themselves. Then we are going to implement the JavaScript part so all of this works in the end, and that is going to be the final magic flow. So how does this work right now? I can delete the entire tree, which means if I click delete, the root node is going to be highlighted and then this tree is going to be destroyed. So let's do it. Do you see? It was highlighted and then the whole tree was destroyed. Luckily, if I refresh, all of my things come back. So this is not storing this persistently anywhere right now. Now I could add any item into the node. For example, let's start with the beginning. Let's say if I say 11, then it's going to add that as the root node. Now, if I try to add any item which is greater than 11, it's going to go towards the right side. So if I say 15, that's going to go towards the right side. But if I add another item which is lesser than 11, that's going to go to the left side. So let's say if we say 9, that's going to go to the left side. Similarly, if I say 10, that would mean that it's going to traverse through this tree. So first of all, it's going to go to 11. Then it would understand that, hey, 10 is less than 11. So it's going to come towards this way. Then it's going to check 9 actually is lesser than 10, which means 10 is greater than 9. So it's going to come towards the right side. And this is the exact place where 10 would be added in the end. So let's try this out. So I'm going to add the value 10 here and see where this goes. So here you see that exactly at the place where I told it would be. Similarly, if I add like the value 8, you see that it goes towards the left. And this is how the BST works right now. Now, if I wanted to remove a node, that is also possible with this implementation. But there are different cases that we are going to look at when we're going to code this. So it could be possible that we are adding or we are removing a node which has no children at all, which makes everything super easy. So for instance, if I remove 15, we have no children to take care of. So if I remove 15 from the tree, it just goes away just like that. But if I have, let's say, an item which has one child, then it becomes a different case. For instance, let's say we insert 15 back and now I also insert 16. So now if I wanted to remove 15, that would mean that this 16 would have to be taken care of. So this 16 would come back to 15, or it would take 15's place because 15 is going to be removed. So let's see what happens if I remove 15. You see that 15 was highlighted, removed, and 16 got replaced. So that is essentially the second case of this whole scenario. The scenario with root node is also quite similar to having no child. Let's suppose the tree only had the root element, then we can just remove that. That's super easy as well. The problem becomes when we are trying to remove a node which has two children, right? So which one is gonna take place of this removing node? So let's say if I remove 9, that would mean that there has to be a node here which is greater than 8. So this 10 would take its place, and that is going to be interesting to implement as well. So let's say if I I remove 9 from the tree, then you would see that 10 would take its place. There you go. Now, there are some technical challenges in when we are going to implement that, but let's concentrate on the demo right now, which is super cool. So we talked about insert node, we talked about remove node. We can actually search an element within this tree. So let's say if I search something that doesn't exist, it would say the node not found. But if I, let's say, search for the value 15, it would go ahead and highlight 15 and show us where it resides right now. Similarly, we can have a look at the min value. Now, in a binary search tree, this becomes an amazing thing that the leftmost tree or the leftmost node in this entire tree is going to be the minimum or the minimum value. So 3 is going to be the minimum value because the way binary tree is structured is that it essentially has the least amount of value or the least value towards the left, and the maximum value is going to be the rightmost tree because that is how it's structured. So if I say minimum value, you see that the value 3 is highlighted. If I say maximum value, it's going to highlight 25 because that's the maximum value that we have. Let's say if we were to remove 25 from the tree, that would mean that we now have 20 as the highest value. So if I say max value, you see that 20 is being highlighted. Now let's talk about how we traverse through this tree, because a tree has different ways on how we can move from the minimum value to the maximum value, or from the leftmost node to the rightmost node, or even have to be the leftmost node where we start from, because these are 3 ways you could traverse a tree to go through all of the nodes within the tree. Let's discuss them one by one. So first we are going to talk about the in-order traversal, which is that we go from the left node and then we go towards the center node or the parent and then the right node. So it would start from here, let's say 3, then it would go to 5, then it would go to 6. So left, top, and then right. Now this becomes the left node because now this is the center one or the top. So you could say left child, parent, and then we are going towards 9, but this 9 itself is a parent. So it's gonna go to 8 first, which means that it goes from 3 to 5 to 6, but then 7, 8, 9, and then 10. So this is how this works. Now, if we have a look at the sequence on how they would be highlighted, let's see what happens. So if I go ahead and press the in-order traversal, let's see what happens. So 3, 5, 6, 7, 8, 9, 10. Exactly what I said. And if I just go towards the console and see the value, because we also log them, you would also see that the value are exactly what I just suggested. So here you can see that we got 3, 5, 6. So it's going from the left, then center, or parent. So left, parent, center. Then we got 7, and then after 7 we get 8. We don't get 9 because we have to get the left one. So we have 8, 9, 10. Then this becomes the center. So 7 is the left. Now this whole tree is done. So it goes to the parent, which is 11. Then it goes to the right one, but it cannot actually get this one because this is now the center one. So it's gonna go towards the left. This is also the center, so it's gonna go to the left one. So from 11 it's gonna go to 12, 13, 14. So you can see here that after 10, or actually after 11, we have 12, 13, 14. Then it goes to 15 because now it's the center. Then instead of going towards 20, it would go towards 18. So 15, 18, 20, 25. So 15, 18, 20, 25. In-order traversal also would show you that it would go in a sequence where the whole tree is sort of, you could call it the in-order tree traversal also would show you in a form of the sorted values of the tree, because it starts from the left one and goes from the center to right. And the in-order traversal would also show you that the output is in the sequence of the ascending order, which is sorted, because it starts from the left one, then it goes towards the center one, and then it goes towards the right one. And that is how in-order traversal works. Now let's talk about how pre-order traversal works. In the pre-order traversal, we first get the center one, then we get the left, and then we get the right, which means that it's gonna start from 11, then it's going to go towards 7. All right, so center, then this becomes the center, so it goes towards the center, which is gonna take 5 first, then 3, then 6. So center, 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 left, right, then it's gonna take the center, left, right. So that means 11, 7, 5, 3, 6, 9, 8, 10. This is what we are looking at in terms of how this would work. So if I now run the pre-order traversal, let's see what happens. We are going to see the highlights and also the log into the console. So if I highlight this, let's see what happens. Pre-order traversal. You see exactly the pattern that I suggested. So it starts from the top and then goes all the way. So as I said before, it starts with 11 and then it goes towards 7, 5, 3. So 11, 7, 5, 3, then 6, and then 9 because this is the center one, and then left and right. So center, left, right, center, 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 left, right, center, left, right. Then it's going to be take the center, but then it's going to go to 15, which is a center, center, left, right, center, left, right, and that's it. So in the end, we are getting 20, 18, and 25, and you see the same values here, 20, 18, and 25. Now let's talk about the last method of traversal and how that works. In the last method, which is post-order traversal, we essentially first get the left and right, then we get the center. So the center or the parent is essentially essentially at the end. So which means that we are going to start from the left and then the right, and then so here it would start from 3, 6, and then it would go to 5 because left, right, and center. Now this is essentially the left one, so it's gonna go towards here, but it cannot go to the center first or the parent first, so it's going to go towards 8, then 10, then 9, then it's going to go towards 7, and then it goes all the way here to 12, then 14, then 13. Similarly, it's gonna go towards the center one, but here it has to go towards the right one first, so it's gonna go here 18, 25, 20, then 15, and then 11. So 11 comes at the end in this whole journey. So if we run post-order traversal, let's see what happens. So you see left, right, center, center, left, right, center, left, right, center, and that is the entire journey that I just explained. So if we have a look at output as well, you can see that it starts from 3, then 6, then 5, similarly then 8, 10, 9, and then 7, and then we have 12, 14, 13, then 18, 25, 20, 15, and 11. So that is the whole structure on how this whole tree works in terms of traversal. And having said that, I believe now you have a complete picture of how the binary search tree works, but now I'm going to explain to you how to implement that in JavaScript. But before we do that, again a reminder, if you have not subscribed to the channel or liked the video, please do both of them because this would help this video go out to a lot of people which would benefit from this video. Now we can get into how to implement this in JavaScript. Let's go. Alright, so first of all, what you need to do to implement this is that you need to clone this repository. So it's github.com/ahsanayaz/fun-with-javascript. You go to this site and then you should be able to copy this link. Obviously, this site's link is in the description of this video, so you can get it from there. Then you need to open your terminal and you need to type git clone and then you need to type this URL. Once you do so, this will create a folder named Fun with JavaScript into wherever you are trying to run this command from or whichever folder you are in. And I'm assuming that you have git installed in your machine, obviously, because so once you have done all of that, all you need to do is you need to open this into your favorite editor. I'm going to be using Visual Studio Code here. And once you have done that, you need to just open the terminal. You can do that by clicking here and then you can say new terminal and this should open this window for you. And now you need to switch to a branch that I've created just for you. It's called BST start. So you need to do git checkout and then BST start. Once you do so, you will see a bit of changes in the files and I'm going to explain you what we are doing here. So you need to go to the source folder project. Inside we have JS binary search tree. This is the folder we are going to be looking at. An overview of this folder is that we have the index.html where we have our template. We have the binary search tree.javascript which has our BST class or our tree class which we are going to work on. Then we have the CSS file for just some stylings and we got the main.js from where everything is executed right now. But we also have the BST UI.js which essentially wraps around the HTML and the buttons that you saw, and when we click on those buttons, this file handles what happens. So if you're interested in knowing how I built all of this or these buttons, let me know in the comments and I might create a video on that as well. But let's get into the JavaScript file and how to run this project. So once you have installed all of this, once you have checked out the branch, you need to run yarn or you need to run the npm install command. So npm install. Once you have done that, you should see a node modules folder in your workspace. And once you see that, then all you need to run is npm start or yarn start. This should essentially start the webpack server at localhost 8080. And now we can see our branch working. So if you go to localhost 8080, you will see exactly the same thing as what I showed you before. Now this is just running locally. So if you go to binary search tree, you're actually going to start looking at some errors because our binary search tree implementation is not implemented yet. It's trying to execute a function which doesn't exist. So what I'm going to do now is that we are going to work on the tree itself and go through how to implement the binary search tree in JavaScript. I'm going to go to JS binary search tree, and in here we have this file called JS binary search tree which has some code implemented. Let me show you or let me tell you what we have right now. First of all, you notice that when we are working with the binary search tree and when we have to insert a node, we do check if the value that is being inserted right now is less than the current node or the parent node or it is greater than. This is called comparison, and we have a function here for comparing if the node is greater or lesser than the current node. So here you would see that we get two values and we just compare if they are equal or if the first value provided is less than the second value. So we are going to be comparing a node, a value that we are going to add to the tree with an existing node to see if it goes towards the left side or the right side. Now you can see that we also have some comparison constant here that essentially is being used here as well. But then we have this tree node class which is going to be each node that we add to this tree. So let's first start with the tree node class and I'm going to explain what that is. So we got this BST tree node class and essentially this has a constructor which takes two things. One, a value, and second, a parent. So when we are going to create a node, it would either have a parent or not. If it doesn't have a parent, that means that we are talking about the root node right now, because the root node doesn't have a parent. But any other node in this whole tree has to have a parent, because that's what it is going to be. Each node can have a left child and a right child, or it could have null set to that, which means that it doesn't have that particular child. There could also be nodes which have both of them set to null, which means that they won't have any child. Finally, each node would have a value. As we saw in the tree, we have 11, 7, 9. All of these are values that we are talking about. If we talk about this node 5 here, the parent of this node is 7. The left child of this node is 3. The right child is 6. So that's how we are going to manage all of. Now we also have some helper functions. For example, we have a function or a getter to check if this node is a leaf, and we call a node a leaf if it does not have any children. So here 12 is a leaf, 14 is a leaf, 13 is not a leaf. Every element or every node in the tree which does not have any children is going to be considered a leaf. Similarly, we have its opposite, which is has children, and that is just essentially returning the negative of its leaf or is leaf, which is telling that hey, this has a child. Now that we have said that, let's add the functions that we need for the binary search tree. So I'm going to quickly add those. So here we have a couple of functions and some properties as well. First of all, you see that this binary search tree has a compare function, and by default the value of this compare function is going to be default compare number function, in which we are understanding or we are assuming that every value in this tree is a number. So 11 is a number, 7 is a number, and whatnot, and we assume this and then we compare them. So we cannot compare a string with greater than or lesser, because that would result in a lot of issues. So we are comparing them here, and I think I should be actually using the triple equals to here as well. Now let's talk about some of the properties in the binary search tree. So here you see that we have the root variable, which will essentially hold the tree itself. So it will hold the root, which would have children, and those children would have going to create a tree structure. Then we have the compare function that we already discussed about. So this constructor here takes a compare function and then it does some magic that we are going to write. Then we have a method for inserting a node, removing a particular value or a particular node. Then we search a node by its value. Then we have a min function, which essentially returns back the minimum value of the node. We have the maximum function, which returns the maximum value of the node. Then we have three methods for the three traversal types that we discussed. So let's talk about what happens when we create this binary search tree. So whenever we use the constructor to create a new binary search tree, two things are going to happen. First, we are going to assign the root with null, which means that there's not going to be any node inside this tree. And secondly, whatever compare function the developer provides here is going to be assigned to the compare function, because this compare function is going to be used later on in the code. As I said, by default it aligns with our function that we already have, so this is going to most likely use that. Now if I go ahead into the main.js, you will see that in the main.js at line 33 we are creating a new binary search tree without providing any compare function. So that would mean my tree here is going to have the root set to null. Now if I save this file and if I run this on localhost and refresh, you will see that at least we are going to get rid of all the errors that we had. So if I go to console, we are not seeing any errors, but we don't have anything to work on because we have not implemented the functions completely. Now we are going to look at the insert method. Actually, I should be removing all of these nodes. So let me quickly do that. So if I refresh now and if I open console, first of all, we are going to implement the functionality when this whole tree is empty and we add something. So if I add 11, that just goes into the tree, and that is what we need to implement first. So to do that, all we need to do is this. We are going to initially say that, hey, we take the node or we create a variable node and we take this dot root. By default, when we are going to do that, when there's nothing in the tree, it's going to take the root value, which is null. So it's going to be null. Then we are checking, hey, is the node null? If that's the case, then we essentially create a new node with the value that is being provided. So let's say if we are adding the value 11, it's going to go inside this tree node. It's going to assign the value, the string value essentially, and then it would essentially assign that to the this dot root property, and then it returns this dot root, and that's what it does right now. So if we go back to our local host, you would see that at least one node would be inserted because we implemented one condition. So if I refresh now, you will see that the 11 property has been inserted, and we add a lot of things, but we have just implemented one condition. That's why we only have one node right now. Now we need to implement the other conditions, and as I said before, we are going to have to check each node and we are going to have to see where the value that we are adding actually ends up. So as I said before, we need to check each node and see its left or right possibility. We check if the current value that we are providing as a new element, does it go towards the left or the right? So let's write the code for it right now. Alright, so we'll start with the comparison first. So we are going to check, hey, is the value that we are providing deciding, we are going to compare this using the node.value. So first of all, we are taking the root itself. So we are starting from the root and we are checking, hey, is the value equal to the root or not? In this comparison, we are either going to get equal, lesser, or greater, just like these. So equal is smaller or greater. So we are going to check for each condition and handle each case. First of all, let's say if this is equal, then that would mean that if we find a node that we are trying to add and that already exists in the node, then we don't need to add it because that node is already present. So we are going to just say inserted node equals to node and then we just return it. We do not add or create a new node. Now let's say that we got the comparison and we found out that the value to be added is smaller than a particular node. Then we have to go towards the left side of it. So how do we do that? We check if the comparison is smaller, then we check if the left node is it null or not. If the left node is null, then it's super easy. We just replace null with the value that we want to add by creating a new node. So if it's null, then we create a new tree node and then we save that into this variable that we are going to use later. But essentially we create a new node. Then all we need to do is that we just need to say node.left equals whatever node we have created. So we say node.left equals to inserted node and then we return back true here. And I'm going to tell you why do we return true here. So if that's not the case, which means that let's say this node.left was not null. Now that's the hard part. If that's not the case, then that means that we need to go further into the tree and find out where we need to place this. For example, let's suppose I add the value 1 here. That would mean it would come to 11 from the root node. Then it would say, hey, is 1 less than 11 or greater than 11? It's less than. So now it has to go to the left, but this left node is not null. That would mean that since it is not null, it now has to check for the value 7. It's going to check, hey, is 1 less than 7 or not? Obviously it is. So now it goes towards the left, but this is also not null. So it has to now check 5 and similarly check 3. Finally, when it would check, hey, 3 doesn't have a left child and 1 is less than 3, it would go and create a node here. That's what happens right now. So if I create, let's say the value 1 here, you see that's where it is created. So as I said, if the node's left is not null, then we need to keep going towards the left node one by one. And that is why I'm using a true here because I'm going to use a while loop in just a bit. Now let's say that the comparison told us that it's not smaller and it's greater, which means the value that we are trying to add is greater than the node that we are trying to compare with. That would mean we need to implement another else if condition. And here we are going to first check similarly if the node doesn't have a right child. If that's the case, then we create a new node and we similarly say node.right is going to be the inserted node and we are going to return true. But let's say if the node's right element is not null, then we need to keep scrolling towards the right one until we find a suitable solution. So here we say node equals to node.right. Now that we have all of this created, let me add a while loop around this. So I'm going to be adding the while loop here and here I'm going to say while true and then we are going to keep going. So when we say while true here, that means that until we return something from here, this whole loop is going to run on and on and on again. Now the problem here is that we are returning true from here, which means that we're returning it from this while loop, but essentially from this whole function, which is not true. We shouldn't be returning true itself from here, but we should be returning the node that we are creating. So what I'm going to do is that I'm going to wrap all of this while loop inside an immediately creating function or an IIFE, whatever you want to call it. And then we are going to use that. So I'm going to create another variable here and I'm going to say const node inserted, and don't confuse it with the inserted node because these two are different. But I'm going to create a function that essentially calls itself immediately. So I'm going to create it just like this. So this is calling itself. And now in here, we can have the while loop. Now I can check if this has a value, then we return the inserted node, right? So now that we have this, that would mean that we got a node that we wanted to insert and that is supposed to work absolutely fine. Now let's go and try this out. So I'm going to go to my localhost here. And then if I refresh, you see we create all of the nodes because we already have the code there and it is doing that automatically. Now if I add a node, let's say 1, you see that it comes all the way here. Now if we wanted to debug this, that would be so much fun. So what I'm going to do is that I'm going to essentially do this and then I'm going to refresh this and let's quickly see what happens happens when we debug this, and I'm assuming that Webpack is going to allow me to do so. So let's say if we do binary search tree.js, then I'm going to go quickly into this insert situation, and here I'm going to put a breakpoint here, a breakpoint here, a breakpoint here as well. Let's see, and we got this as well. And now we are going to just say that, hey, insert the value 1 inside this tree. So let's start with okay. And now I'm going to bring this up and see what happens. So first of all, what's happening here is that we have this node that we are trying to add. So the value is 1. Okay. The node that we are beginning with essentially is the root node. As you can see, the root node is 11, as we already discussed. So we have 11 as the root node. Now it's comparing it and it's saying, hey, this is -1, which means that it now has to go to the left side. So since it's left side, it's going to go to the smaller one. It's going to check is the left null or not. And now we know that the node's left is 7, which is this exactly node. So now it has to go further into the tree. So it's going to go forward. And here you see we do node equals node.left, which essentially just says that, hey, instead of checking 11 right now, which is this one, now start checking the left one, which is 7. So it's going to now rerun the loop with the value 7. So now it compares this with 7. Similarly, it's going to go ahead and then it's going to compare it with 5. So here you see that now it's comparing with 5. Similarly, it's going to compare it with 3. So now it compares with 3. And finally, it would say that, hey, this is smaller. Yes. Does this element have a left child? And that is not true. So this node has a left set to null. That's why it's going to come here and then return true from here. That's why we are going to end this loop. It's going to jump to the node inserted. You see here. So we got the node inserted. And since we have that, it would essentially take the node back, and finally we have this node created here. Now it's going to be the same case if you want to add anything towards the right side. So it's exactly the same. Now let's talk about the other functions that we can work on really quick. So we are going to start with the min function, and the concept of the min function is that it needs to return the leftmost element in the tree, and we can do that really easily. Here's the code. We first check the node itself. So what we do here is that we say that, hey, start from the root node by default if we don't pass a node. So it starts from the root, and then it says, hey, check the node and then keep going left. So we say while current not equals to null and the current left not equals to null, which means that we are trying to go to the leftmost node until its left becomes null, which means that the leftmost child, which doesn't have any more left childs, that's going to be the smallest value. So we keep doing that until finally we get the value, and then we return that value from the min function. That's going to be the same case for Mac. So I can actually copy paste the same code, and here I can replace the left with right, and here I can say right, and here we do exactly the same thing. Now let's test this out. So I'm going to open my DevTools here, and then I'm going to go to sources. So we are going to refresh this first, and then we are going to say min and max. So now let's see what happens. So I'm going to try out with the min value, and then if I say min value, so it starts with the root node, which is 11. The value here is 11. Now it keeps going on. So it checks, hey, current equals to current.left, which means that now it's going to check 7. So now the current becomes the value 7. Then it goes forward, and now the value becomes 5. Similarly, it goes forward, and the value now becomes 3. Now, since the value of current is 3, it's not going to go inside and do anything because it's going to go outside, and now we get the current value, which is 3. Yay! So now that we got this, it's going to highlight this, and we are going to be happy. Similarly, it's going to do the same thing for the max value. So it's going to keep going until it actually gets the value 25. So if I press this again, you see that we are highlighting the value 25 as it is found. Now let's talk about some other functions that we have to discuss, which are essentially the traversal. So the in-order traversal, the post-order traversal, and the pre-order traversal. In the main file or in the deployed version, obviously all of this works. So if I can check in order, you can see that all of them are being highlighted. Now, how do we actually implement them? The implementation of them is actually much easier than I actually thought, but when you don't know things, it's actually very difficult. So we are going to start with the in-order traversal, and inside here, you notice that we use a node, and then we also have a traversed array. And the traversed array is because we want to return all of the nodes in form of an array, which we actually log in our main file as well, that you might have already noticed that we always log the array. Now, the code for this is this. So we essentially start with the node, and how this code works is that we essentially start with the root node, and we go node by node, and we run this in a recursive manner. You can see that the in-order traverse is being called within the function itself, which means means we are using recursion here, and we have to have an exiting clause inside this whole recursion. So the one exiting clause that we have is this one. We essentially check, hey, if the current node is null, which means that there is going to be a point where the right is going to be null or the left is going to be null. That's where we exit this. So here we say if the node is null, then we return the array itself. Now let's say we had only one item, which is the root inside this whole tree, then that would mean that it's just going to take the root. It's not going to see node left because it doesn't have a child. Similarly, the node right is not going to be the one, but this will push the node itself inside the traversed array and will return one item in the array. If we have a tree which has nothing, that means the node is null, or this dot root is null. That would mean that it would just return the empty array. But if the node or the root node has childs or children, let's say node dot left and node dot right, then we essentially repeat this process with using recursion. So here you see that we say if a particular node has a left child, then we also want to push that child inside this traversed array, and that's how it works. So when we use the same function for recursion, then we are pushing that node inside this function so that node's children are also evaluated. So it goes in a tree manner all the way from top to bottom. Let's actually test this out and you would understand more on what I'm talking about. So just to revise, the in-order traversal works in a way that is left, center, and right, which means that left parent and then right children. So here, if I refresh now, we are going to inspect this. We're going to go and just put a breakpoint after refreshing. So I'm gonna remove all of these. Then I'm gonna put some breakpoints right here. And now let's see what happens. So here, if I start working with the in-order traversal, let's see what happens. First of all, as I said, the node is going to be the root node. So we are taking with 11, and we said that the first node is going to be the left node. So we already know that the first item going to be pushed into this traversed array is going to be 3, because we start with left, then we go right, and then we go center. Actually, that's wrong. It's left, center, and then right. So it's going to go inside here. Then you see that it says, hey, node dot left, it already exists. So we recall this method now with the node left, which is value 7. So if I hit the play button, you would see that now the node is 7. So it's gone from 11 to 7 already. Now it's going to go ahead and now it's going to go with 5. So it's coming inside 5. Then it goes further inside with the value 3. So it goes further inside. Now that it's gone inside 3, we already know that this node that we have, it doesn't have a left value. The array is still empty. So if we go forward, you would see that the left one is not executed. We are pushing this particular node, the value 3, inside the traversed array. So if I go forward, you see that the traversed array now has the value 3. There we go. The left and the right, they are not going to work. Similarly, if we go forward, then the next value should be 6. So here the value that we are going to push, actually 5, because it's left, center, and right. I keep forgetting. So the next value is 5. Similarly, the next value is going to be 6. So if I push forward, you see that now we are using the value 6 here, and that's what going to be pushed in the array. So far we have, so if we go forward, you would see that here we are pushing the node, and now if we go forward and see traverse, we got 3, 5, and 6. So that's how all of this working, and this would keep on going until we have all the values that are being highlighted also added in this whole array. So we have that array now working. Now the fun part is that the other implementations of the other traversal are exactly similar to this one. So I'm going to be copying this, and we are going to be replacing this with the correct values by just modifying when what happened. So for the in-order traverse, we know that we go left, center, or parent, and then right. But for pre-order, we first go with center, then left, then right. So I'm going to move this from here to actually here. And that is all I need to change apart from the functions as well. I'm going to just copy this function and use this. And now let's talk about the post-order traversal. In this one, we go with left first, then right, and then the center one. So I'm going to cut this one and move this after the right one. And I'm going to change the functions as well. So now let's save this and try this out. So I'm going to refresh my localhost here. And now let's say in-order traversal. So left, center, right. Then we got the pre-order traversal, which has center first and then left and right. So center, left, right, center, left, right, center, left, right, center, left, right. And now we have post-order traversal, in which we have left, right, then center. So if I say post-order, so left, right, center, left, right, center, left, right, center, left, right, center. And now it's going all the way. So that's amazing. We have implemented all of the things that we talked about, except for the search method and the remove method, which is going to be a bit complex. So let's first talk about search method. We already know that we have a lot of traversals that we can work with, but we are going to pick the post order traversal here. So all we need to do here is that we can say return this dot post order traverse. So we are traversing all of this, and we already know that this post order traverse essentially takes the root itself. So we don't need to pass anything from here, but then we just need to use the find method, and here we say node, and here we say node dot value equals to the value that we are searching for. So if we implement this, the search is actually implemented. So let's go and check this out. So I'm going to refresh this now, and let's say if we try to search the value 15, what would happen? We find it. Similarly, if I try to search the value 9, there we go, we find it. So the search is implemented now. So for the remove method, we have a couple of cases that we are going to implement. So first, we are going to essentially check, hey, is the value that we are trying to remove, does that exist in our tree or not? So we could either pass the node itself that we want to remove, and that would mean that it exists. But if you're not passing the node, then we are passing the value, and we search the value. So we essentially get back the node itself. So you can see that here we actually use the find method, which should return the search node. Now there are a couple of cases that we need to cater. If the node is not existent, then we just return null, which means we are not removing anything from this tree. But let's talk about the first case where the node could be a root, or it could be essentially a node which is a leaf, which means that it doesn't have any childrens at all. And that would mean we need to create a couple of utility properties or utility variables. The first one is going to be the root node check. So we can check if a node is a root node by checking what is the parent. If the parent is null, then we know that it's the root node. Then we are also going to have a variable to check if the node has both children or not, which means that the node's left should not be null, it should be a node, and the node's right should not be null, it should have a node. Similarly, we are going to check if this is a left child or right child, which means that the node that I'm trying to remove right now, is it the left child of its parent or is it the right child of its parent, because we are going to use that in one of the conditions. Now let's talk about the first condition, in which we say that this node is a leaf, which means that it has no children at all. So we're going to first check, let's say the condition becomes that we have the entire tree gone. Let's say we have one node. Now this root node itself is a leaf because it doesn't have any children. So that is the first case. Then there could be another case. So let's say we add 12 here. Now this 12 doesn't have any children. So this also is a leaf. If we remove 12, that means that we are just removing 12. Let's actually do one more. So let's say we also have a node that is 13. Let's say if we are removing 13, then it doesn't matter what 11 and 12 does, because we are just removing 13 and the rest of the tree remains the same. So let's say if we are removing 13, nothing else happens. Similarly, if we only have the value 11 or the root node and we try to remove the root node, then we just make it null. So these are two cases when a node that we're trying to remove is a leaf. So again, as I said, the root can be a leaf as well. So in this case, when this node that we're trying to remove is the root node, we just set the root to null, and that is enough. We don't need to do anything else. But if you're talking about another node that is a leaf, then we need to check if that particular node is a left child or the right child. And the reason for that is that let's say we have a situation where we remove, let's say 25. So in this case, if we have a leaf that is 18 and we're trying to remove this, then we have to check, hey, is this particular leaf the left child or the right child of its parent 20? Because in order to remove this node from the tree, we need to set the left property of 20 to null, because that's how this is going to be removed from the tree. So we need to identify, hey, do we need to set the parent's left property or the right property? And that's what we are doing in this code right now. So we are checking if this particular node that we are talking about, is it the left child of its parent or the right child? We could have used the left child property as well here, but I'm going to modify that later on. So if this is the left child of its parent, then we just point the parent's left to null, which means that this node will no longer exist in its parent's left property. Otherwise, if this is not the left child, then that means this is the right child, and we just need to do exactly the same. So we will set the parent's right pointer to null, which means this element is going to be removed. And finally, we return the node, so we know that this node is being removed. So if we save this and if we go forward, so if we save this and go forward and refresh, let's see what happens. So we are going to check both of the things. First of all, we are removing the entire tree. Then let's say we have a situation where we have, but let's say 11, and then we have 13, and then we have 12. So in this case, this 12 is the node that we want to remove, and this is localhost. So this is what we implemented right now. So if I try to remove 12, that should mean that this 11 and 13 would be remaining. So if I click OK, this highlights and removes it. Super cool. Now, if I try to remove 11, what would happen? We have not implemented the case where we have a different situation. So if I try to remove 11, 11, it says element not found. So we're not gonna look at that. So I'm gonna remove delete now, or delete the tree and add 11. And if I try to remove 11 now, which is a leaf, it works, no problem at all. So our both cases that we just implemented are working now. Now let's talk about the case where we have this not as a leaf, which means that there is at least one child in this particular node that we are trying to remove. So we are going to cater the case where it doesn't have two childs or two children, but only one child. So we are going to put a condition for not has both children, which means that it has one of the children's, either the left one or the right one. So first of all, we are going to create a variable in which we take either the left child or the right child, because it doesn't have both children, which means that either the left is going to be null or the right one is going to be null, and the other one would be a node in this case, right? So let's say we have a situation in this tree where we have to remove 20. Now this 20 has 18 as the left, but its right is null. So that means we are taking out this 18 from this code just like this, because we are checking node.left not equals to null. It's not null, it's 18. So it takes out the node.left. Now we check if this particular node is the root node, and that makes things easier for us, because let's suppose if we don't have any item in the tree and we have 11, and then let's say we have 10 here, that would mean that we have this left child here of 11. If I need to remove 11, then this 10 becomes 11, or this 10 takes the place of 11. That's what I'm trying to say. So it's easy because we just have to move one node up, and that is super easy. So if that's the case, then what we do is that we check. So if this is the root, then all we need to do is assign this child towards the root. So we just need to change the root itself. So we can simply say this dot root equals to child. So we found the child, we got it in the variable, and we replaced the root with child because we are removing the root itself. Again, if I show you this example, that means that we are removing 11, so the root would become 10. So if I remove the node 11 here, you can see that the root becomes 10. But let's say that's not the case and we have an element that is deep down in the tree that's not the root, then we have a child. So what we are going to check then is that if this is a left child that we are talking about, or if it's the right child. Let's suppose if it's the left child, and that would mean we have something like this. So I'm going to go to insert node, and let's say we add 9, and then we also add, let's say 8, right? In this case, if we have this 9 as what we are talking about, and this has to be removed, then that would mean that this 8 would take its place. That would mean that the 10's left property becomes 8. So 10 would start pointing to 8. So if I remove, let's say 9 from here, let's see what happens. So 9 is highlighted, remove, and now the left of 10 is 8. That's what we need to do. So here we are going to check if this is the left child, then just make sure that the node that we are trying to remove, its parents left points to child. So we got 10, we got 11, let's say, then we got 10, then we got 9. Now this means that if I'm removing 10, I want this 10's parent left, or this 10's parent's left property to point to 9. So we are saying node, the node that we want to remove, its parent's left should point to child, or this node's child, and that's what we are doing. If that's not the left child, then we just do the same thing with the right child, and this should start working now. So if I try to save this now, and also we need to return the node from here as well. So we do child.parent equals to node.parent, and that's also important because we need to update the child as well. So when we remove 10 from here, we point 11's left to 9, but that 9's parent should also become 11 because 10 is being removed from the middle. So that's what we do at the end here. And finally, we return the node that we have removed right now. So I'm going to save this now, and we are going to try this locally if this works. So we are going to delete the tree. We are going to add 11, also going to add a new value called 10, and then we are going to add another value called 9. And now if I remove 10, this 11 should have a left that points to 9, and 9's parent should become 11. So if I remove node 10, then you see that it works. So our implementation is working fine now. Removing a node that has both of the children, and that is a bit tricky. And the reason for that is that if I remove this 7 from here, then that would mean that we need to have an element here instead of 7 that is greater than 5, but it's going to be lesser than the next value that we want to point at. So that would mean that this 8 is supposed to come here. So it's going to be 5, 8, but then 9 is since greater than 8, so that would make sense. So I cannot have 9 here. I cannot have other values here. It has to be 8 because after 5 it comes 8 and then the rest of the values, right? That's how the binary search tree works. So it doesn't matter which value I'm removing. If it has 2 children, then the next value as a pattern is supposedly something like this. So if I'm removing 15, let's actually add one more node, so it makes more sense. Let's say we have 15, but then we have 18. So let's add actually 17 and also 16. So that would essentially make these two things. Now here, the concept is really interesting. If I have to remove 15, I have to make sure that I go to the right side of 15, which means that from 15, I'm going to go to the right tree, this one. And then in this tree, I'm going to find the least value, which means I have to go towards the left side of the tree as much as possible. The least value that I can find here, this is going to replace 15 because that is essentially the next greater value than 15. So I need to do all of this to make sure that I replace this with the correct one. And that would happen actually into our final deployment. Let's say if we add those nodes, so we say something like 17, then we also add another one 16. So let's say if I want to remove 15, then 16 would take its place. So if I remove this, you see that 16 is now here. Similarly, if I remove 16, 17 is gonna come. If I remove 17, 18 is gonna come. If I remove 18, 20 is gonna come, and that goes on and on and on, right? So that's how it works. So we're gonna go to our code now and write the final condition. So it is something like this. First of all, we are trying to get this least amount of value by saying that, hey, you want to remove 16, then let's go to this node and try to find the minimum value of this node. So instead of using the root where we already use this minimum value, we use it with the root now, but now we are going to use the same minimum value function but with this node, which is the right node of the node to be removed. So we're gonna go to the code and say, hey, this dot min function is gonna be called with this node to be removed right value, which is exactly what we just talked about. Then we're trying to find here is that this minimum right leaf, which is the value that is here, is this the left child of this element or the right child of this element, right? Because this is important as well. Now the thing is that this 18 here is right now this value, but there could be a reason where this 17 is not there, but we have some other value. So what do we do here? Let's say we remove the node 17 here, and let's say we add a new node and we call it 19. Okay. Now if I remove 16, what should happen? Let's say if we remove 16, let's see what happens. So here we got the 18 value, but we also got rid of 19, and that is what happened. So what we need to do here is that we need to check what is the minimum right leaf. We check if the parent's left is this. Then what we need to do is that we say minimum right leaf dot parent dot left equals to null, which means that we are just setting the value to null. In this case, let's say if we are trying to remove 15, then we are saying, hey, this 15 is going to be removed, but we need to put 18 here. So 20's left is going to be null. So that's what we do here. We say that, hey, parent, which is 20, its left is going to be null. Similarly, if that's not the left child, then we do the same thing with the right one. So we say that, hey, if that's not the case, then the right item or the right child is going to be null. Finally, what we need to do is that we need to make a clone of this node that we are trying to remove. Why? Let me show you. So what we do is that we say, hey, this node that we are trying to remove, which is 15, we are going to replace its value 15 with this value, which is 18. So we just take the value out here and then we replace it. Why do we do that? Why do we don't replace the whole node? Because this node already has a parent, it already has a child, it has whole structure here. If we remove this node and we replace all of this here, then we have to set the left, right, the parent, and all of that. So instead of doing all of that, we just create a clone and then we just assign this value to this one. And that's what we're doing here. Finally, when we have set the value, we return the clone, and that's so now if I refresh this, we can try this out. I'm gonna add a new value here. So let's say we add the value 16 now. So we are adding 16 here. And now if I want to remove 20, then the least value is 25. So if I remove 20, 25 is going to take its place. Now, if I say I am going to remove 15, then 16 is gonna come up all the way. So if I remove 15, you see 16 came up all the way. We got then 25 and then 18, and everything works perfectly fine. And that actually marks the point where we have implemented all of our functions. I'm just gonna do one little thing because otherwise my soul would not rest in peace. And that is we had this is left child and I think we didn't use it properly. So this is where we are going to use this. So we are going to check if this is left child, then we do that and I think we should be good. So what we are going to do is that we are going to quickly test this out. So I'm gonna say, hey, let's say if we have an item, so we are going to first remove, let's say 25. So now we are saying that, hey, I'm gonna remove this 8 18 from here, which is essentially, I think this one. So node is leaf and then is left child. Yes, exactly. So I'm going to simply say 18 here and then it should just remove this. There we go. This worked. And now I can push this and you should be able to get this on GitHub. All right. So I hope that you liked the video. If you did, press the thumbs up button. I don't think anyone explains in so much detail with so much visual examples that you can try out for yourself. So if you appreciate the work that I'm doing, consider becoming a supporter. You can also chime in on the streams that I do every Wednesday and Saturday. We do live coding and learn a lot of things. So if you fancy all of that, join us. And as always, happy coding, and I'm going to see you in the next one.